right, welcome back, and we are moving on now. We're bringing in this phenomenon called the Doppler effect. Okay, now Doppler effect, what is this? This is one phenomenon in science that was introduced by a scientist called Christian Doppler. He was an Austrian physicist, and he came up with this theory around, or this phenomenon around 1842. Okay, now Doppler effect, what is it? Doppler effect is the apparent change in the frequency of the wave as the source and the observer move relative to each other. Okay, so when a wave like sound wave, for example, is moving in air, okay, how the person hears the wave, because hears the sound, because what you hear is related to what we call the pitch. And the pitch is actually the frequency of the wave. So what you perceive as the pitch of that sound may either be greater than the pitch of the source or less than the pitch of the source, depending on the conditions at that moment. And we are going to elaborate this. I'm going to explain further on this one. So remember, and always remember, that pitch is actually the frequency of the wave. Okay, now looking at sound waves, for example, if this represents a source of some sound, this sound, because it's a wave, has got some frequency. Okay, now if it is moving in this direction as it is shown, and there is an observer here at point A, there is somebody who's listening to this sound as produced by this source here. The frequency that this person is going to hear is greater than the frequency of the source. Why? Because this source is moving towards the observer, and as you can see here, this bunching up of waves there tells you that you have got shorter wavelength and higher frequencies. So this person here hears a higher frequency than the actual frequency of that source. On the other hand, an observer at point B, where the source is moving away, so this one is for the source relative to B is moving away, and the source relative to A is moving towards here, towards A. For B, source moving away, this part here we've got longer wavelength, and that means lower frequencies. So the person standing at position B will actually hear a frequency less than the frequency of the source. Okay, and that is what Doppler effect is all about. Okay, the apparent change in the frequency of the source as the source and the observer move relative to each other. Okay, next, just quick explanations around here. Here is a car not moving, producing sound. Okay, if there is an observer here at point A, okay, and an observer here at point B, both stationary. The observers are stationary, the car is also stationary. Both of them will hear the actual frequency of the source of sound here. So frequency of the source, even the observer hears the frequency of the source, even the observer there hears the frequency of the source, because the source is not moving, the observers are also not moving. Remember, Doppler effect happens when there is motion of the source and the observer relative to each other. Here the car is moving, observer here would hear a frequency greater than that of the source. You can see the bunching up of waves there. Here waves moving further away from each other. A stationary observer at point B would hear a frequency less than the frequency of the source. Okay, in this case here, we're just showing you to say, if the speed is even much bigger, you create more, you're actually making that observed frequency by the person at point A much bigger than the frequency of the source, whilst this side you're making it much lesser than the frequency of the source. Okay. Now, when we talk this Doppler effect, can we actually find out what are those observed frequencies by the listeners as these sources move towards them and as these sources move away from them? the listeners. Both of them, of course, stationary. We're still looking at listeners stationary. Can we do that? Or put differently, if it is it's actually the listeners that are moving towards the source or away from the source, with the source stationary, what then happens? We are going to actually look at that and see how we can come up with a Doppler effect equation to help us solve and find out exactly what frequencies are going to be observed by these listeners. Say, for example, you have got this situation where the source is moving towards or away relative to the air, okay, with this listener being stationary. So the listener is not moving. It is the source that is moving either away or towards the listener. Okay, this equation we're going to use is this one. FL equals V. Remember, V here is the velocity of sound in air. If we're looking at air in this case, where it's some sound produced by something moving towards an observer or away from the observer. So the observer is not moving, we put it up there, so its velocity is 0, so it will be velocity of the sound divided by velocity of the sound plus minus Vs. If it is moving towards, we're going to take a minus here, because the frequency here must be greater than the frequency of the source. If it is moving away, we're going to take a plus so that the frequency is less than the frequency of the source. Okay, now see you in the next section.